My name's Ron Minnich. I'm a software engineer at Google, and I'm going to talk about Orboot on the AMD 64 Family 17. Orboot is a downstream fork of Coreboot. You've probably already seen Ryan O'Leary's talk, either this year or last year. It's entirely written in Rust. So I'm going to talk about the problem, why we're doing this, the approach we've taken, what works, what doesn't, and next steps. So the Open Compute Platform Foundation has created version 1.1 of what we call Open System Firmware, OSF. And that requires buildable, installable, and redistributable firmware by March 2021 on any system, server system, that has got OCP badging. AMD has made it clear in the OSF meetings over the last year or so that they're not going to be able to meet that date. They don't have a way to distribute a PEI or UEFI for their x86 that can be distributed. They don't have anything like Intel's redistributable blobs. But there is an interesting wrinkle here. The EPIC firmware actually doesn't do all that much compared to what we're all used to in the Coreboot community. And in particular, the EPIC firmware doesn't start up DRAM. That work is done by the ASP, formerly the PSP, which was the platform security processor. And in fact, the x86 BIOS code runs in DRAM. It's actually copied to DRAM. And the DRAM comes, the x86 comes out of reset running in DRAM. Well, what platforms in the x86 do we have that look like a platform with DRAM ready? Well, it looks like a QEMU Q35 target. So for the first thing I did, just to get some idea of where we were, was build QEMU for the AMD board we have, Q35 target. And you can find all this work at github.com, rminich, and my Coreboot fork in any branch named Rome. There are a number of passes at this. So I built Q35 image, dropped it on top of the ROM image, burned it, and got serial output. I should mention, by the way, that in the branches, you can find a simple command interpreter that lets you enable and test APIC timer interrupts, more on why we need that later, and also an implementation of serial ICE built into Coreboot that's not a payload. That's also very handy, works well on the ROM because we have DRAM up. All right, a quick side digression here. What's where? What's in memory? What's not in memory? The ASP copies some part of firmware image to somewhere in RAM. On the AMD CRB we have, which you'll see a picture of later, it copies 3 megabytes to 76 FD 3 zeros. Question is, where does the x86 start up at reset? Does it start up in ROM? Does it start up in RAM? And we think, although we don't really have any good docs on this, that it starts up in RAM at that address or something like it, depending on the board, in 16-bit mode. The code selector is the standard F3 zeros. Now, how does that work? It's running in RAM at this crazy high address. It's not even a valid 16-bit address. Well, shadow segments are set up. Interesting point here. It seems that the ASP can cause that to happen. We're still not sure why those shadow segments are set up correctly, but we know that that starting address can vary from one BIOS to another, and yet the ASP is able to read it and set those up. So the ASP seems to have a lot of ability to control the x86 that we still don't know a lot about. Anyway, this all kind of falls apart, this running in RAM at a very high address, as soon as we try to flip to 32-bit mode. We don't know where we are. So we needed to rethink startup a little. So here's our memory. SPI ROM area very high. DRAM containing some part of what's in the SPI ROM area as determined by the FMAP. Quick note on Orboot, which you may have seen from the earlier talk. The core function or core file in Orboot, the thing around which everything else revolves, is a file called main.rs. It's in the mainboard directory. Everything starts in main.rs. Main.rs defines a lot of critical structures that are on the stack or in a static heap. And main.rs uses these two macros to include a file called bootblock.s. Main.rs assumes we're in a reasonable or almost native address mode. And the x86 in its way causes multiple problems because the x86 starts in 16-bit address mode. So we need a 16 to 32 transition and a 32 to 64 transition. And the complexity of all this, of course, is the reset vector is in the last 16 bytes of memory, be it flash or that RAM area. Would be nicer, all you future architects, start at 0, don't start at high memory. ARM and RISC-V are much easier. So x86 startup always has this backwards bootstrap. You're way up high in memory. You've got to do a relative jump back. That's good if you do a relative jump. That makes you position independent. There was an older form in core boot where we did a long jump to seg and offset. I think that's not really what you want to do anymore because that's not position independent. We go to this thing that's about 32K max of flash, and that's because signed 16-bit, you can only jump back about 32K. And from there, we kind of get into something, a better addressing mode, and then we end up here in Nirvana, where we can address everything. We're in 32 or 64-bit all as well. The approach I decided to take, which is appropriate if the green is Nirvana on the Zen, was to make the middle segment as small as possible. So one issue with core boot and or boot on x86, the APs, the cores started by the bootstrap core, need a 4K aligned SMP startup. So in core boot, we've always shared that between the BSP and the AP. But really that code hasn't changed in decades. There's no reason to have just one copy. We can have 2 copies. It's close enough in what it has always been that it's not a problem to have 2 copies. And so the approach we took here was put the 16 to 32-bit code in the top less than 128 bytes, put any data that code needs in the top 256 bytes, and then we're good to go. If the code is less than 128 bytes, it's within reach of a relative jump with a byte offset. We can have a different boot populator again for SMP. So the red and the yellow are essentially combined into a small 256 byte block, then we jump to Nirvana. And Nirvana, by the way, again, includes the boot block.s in main.rs. So the power on reset rules change just a little. There's a 2-stage jump to the entry of ORBoot, again to the boot block.s. The top 16 bytes have a byte offset relative jump to 32-bit startup. That does the LGDT for 32-bit mode. Then we jump to the boot block.s code. So in a very real sense, we've taken those 3 things and made them 2 things. The first 16-bit mode and 32-bit mode startup is relatively small. And then we can get to the boot block.s, which has a very, very straightforward 32 to 64 inline assembly. And then we're in Rust. That's your big goal. Get to Rust with as little work as you can. So the code at the top 16 bytes is very simple. This is a relative jump back as far as you can go. There's a no-op, and actually what happens is the 32-bit startup comes back here. We do this diagnostic outp to port 80, which is handy if you have a BMC, you can catch it. We load the ASP with some kind of reasonable 32-bit address. Nowadays, actually, we're changing this to hex 2000. We push the start of the boot block, and because of the way we build ORBoot, the boot block's always the first thing. We push the start of that boot block on the stack and rep. These last 2 things are basically an absolute jump. Why do we do this? Because the last step in the assembly of the image is to go and change these 2 bytes. We do not use the linker to do this as we used to do in core boot. The changing linkers and dealing with the LLVM linker turned out to be a little tough. We have a lot of GNU assembly and GLD, I'll call them hacks in core boot that work, but that don't work once you leave the GNU world. What's the code at that 72 look like? Basically, it's written to not be passed through a linker. You only need the assembler. Historically, and this goes back 20 years now, we don't completely trust AS and LD for 16 bits anyway. That goes for double for Rust because the LLVM assembler has some issues with 16-bit. And that's why in the Plan 9 Harvey version, which builds with LLVM, we use hand-coded 16-bit assembly. It's only 35 lines of code. It's dead simple. And it lets us minimize those nasty 16 to 32 artifacts to a small area. We need 0 LD gymnastics. Now we can move on to Orboot itself. So in source, mainboard, AMD, Rome CRB, you can see we follow the Coreboot naming here. One little change, the Rust code following a Rust convention is in source. And then in bootblock.s is the final bit of startup. This is built as part of the Rust build process. The 256 byte area is built independently. The code in here was actually inspired by what we've learned in Plan 9, Coreboot, and Orboot. It's very simple. It sets up a GDT with a 64-bit entry. It enables 4 gig of page tables using gigabyte PTEs. It's 2020. We don't need to worry about 2 meg PTEs only anymore. So the page tables are very simple. They're built at assembly time, not at built runtime. Then it jumps to Rust. So that core code is about 50 instructions. It's basically almost completely position independent. I'm working to make it finally completely position independent. The debugging and comments make it 372 lines. And again, the reason for position independence simplifies in many ways, believe it or not, the assembly, and it greatly simplifies the kind of games we have to play in the linker. So on to Rust. Now the real fun begins. So within a week, I had QEMU Q35 booting on a board. Can't say much more about the board except that it was a board. Since DRAM worked, it was like the QEMU world. I got Linux loading as a payload because this was actually Coreboot at the time when I was doing this, and I had no APIC interrupts. So Linux would hang in the APIC timer calibration. Anyone who's worked with Linux knows that it's great when it works, and when it doesn't work, the debugging is pretty terrible. So all I knew was that I wasn't getting something it needed. At that point, it was actually COVID time. And so I had to take a small reset and move from the board we were using to the AMD customer reference board, which looks like that. So I'm home, I'm isolated. AMD was very kind and was willing to ship us this CRB. You can see it with my MacBook Pro, which runs Linux there. The green Ethernet, that's for the BMC. There is no Ethernet on this board for the main CPU. You have to use USB Ethernet, works fine. It's not a problem. CPU's under there, 1 fan per CPU. You can see those are gigantic fans. And you can see all the power connectors. This takes every single output of this big power supply that there is. So education for me was realizing just how much power you have to pump into these things to get the DRAM going. Important point here, I'm trying to gesture with my mouse. There's a little black header here. That is for what's called the P0 UART. One of the nice things about this processor is there is a UART that comes right off the bootstrap core, doesn't go through any kind of intermediate IO hub or anything like that. It's right off the die, straight through level converters. They nicely put RS-232 level converters on there, and then onto you. So I connected to that. I've been getting serial output for a while. Got no serial output. So the CRB has a BMC, but the legacy chain was not set up right. So if you want, go back and look at my old talk, how to make hardware that is unfriendly to Coreboot. So it's a wonderful board, but little hint, every board should come up with 115.200 baud, and everything's set up so that I can plug in and get serial output if I outbeat a 3FA. So this is for all you hardware vendors out there. Please do this. It makes life a lot better. So sometime later, I was able to get the P0 UART working. Now, the interesting thing, this was a lot of diving around the Coreboot source. And one of the things you learn when you dive around a complex platform with Coreboot, there's an awful lot of code, and it's not always easy to figure out what's where. And some of that code actually runs twice. But in any event, basically, if we read from this IO memory address, set that bit, write it back, we've now set the baud rate default essentially to 115.2. So the basic clock for the UART comes up at 48 megahertz. It needs to be 1.8 megahertz. I think it's a mistake always to have a clock that comes up at a non-legacy baud rate because everybody is hooking these things up. But anyway, that fixed that. And then to get 3F8 decoding, if we don't want to use the memory map.io UART, we do this, bam, we've got serial. And of course, because I like wires and black electrician's tape and wire ties, this is kind of how I hook up to the UART from my Linux laptop there. So I just get endless amusement from this picture. I just had to put it up. Now, we've done this work on 3 platforms, the ASRock A300, which has a, weirdly enough, but nicely enough, I guess, a UART. When you out to port 80, it comes out on the serial port. So it's a little bit odd, but we can work with that. Then we have the AMD CRB. We are moving to working with the MMIO UART on that, which is also known as the P0 UART, processor 0 UART, the one that connects to the CPU die. And then on the third board, the board as I call it, we have 3F8, which works from power on reset. Orbit has this beautiful concept, which we call the driver of drivers. It allows us to gather a bunch of drivers into one. So we're going to create an array, let S equal, it's mutable, which means, you know, it can be changed. You need to do that for the driver model. There's the port 80. We have a port 80 UART driver. We have UART0. This is the 3F8 driver. And we have P0, which is the MMIO driver. 3-element array. We pass this to our driver of drivers device, to the new function, and now we have a console. Every time we write to that console, it will come out on those 3 UARTs. This is the kind of thing, working with Rust, that kind of makes you unwilling to go back to anything else. So this variable is on the stack, no heap, even though it kind of looks dynamic, and the console does exactly what we would want it to do. This is a lot harder in C. And in fact, in coreboot, if you really track it down, it involves CPP, makefiles, kconfig, linker scripts, linker sets, and finally, console code, which calls 5 different UART functions, some or all of which may work, or all of which may actually be doing nothing. So it's really difficult to tell on coreboot by inspecting code what UARTs a main board might actually be using, whereas in Rust, I look at a couple lines of code, I instantly know what UARTs a platform is using. So platform configuration is entirely defined by what is in code in main.rs, and the cargo to TOML is the thing that maps from the use in main.rs to where things actually come from. So loading a kernel. Orbit uses a flattened device tree to manage ROM layout. Ryan, if you see his talk, has probably talked about that decision. We like the FTT because of its ability to nest. You may have seen the changes that went into coreboot for multiple CBFS. Those changes would never have been necessary if we were in FTT. So that was why we started with CBFS and Orbit and moved to FTT. Firmware volume we considered for a couple of seconds and realized that it was a fairly messy, overly complex standard that really didn't do enough. So FTT was the way we went. There was another project we had this summer. Chang-Yun Liu, an intern, PhD student at Purdue in quantum computing of all things, wrote something, I worked with him, called X-Hype. When I say I worked with him, it meant I watched him write a lot of really good Rust code, and then I tested it. X-Hype is a new hypervisor for OSX written in Rust. It follows the Acros virtual machine model. And now we can basically say payload A equals some path to a kernel BZ image make, and now we can load BZ images from the Orbit build. What we need to do eventually is verify that BZ image is part of building, but we haven't gotten there yet. We can, in fact, still use stealth, but increasingly it seems like the world is moving to you're a BZ image or Linux won't boot very well. So that's what we've done. We also needed to generate ACPI. X-Type, well, I should say Chang-Yun also created an ACPI generator. And we're now using this in Orbit with very few changes. Certain Rust crates don't map to bare metal, but otherwise it is fine. And Titus has done that work. Titus is a new employee doing a lot of work on coreboot. So he's ported that ACP generator over and fixed all the bugs that I created in it when I ported it over. So, and it uses the static heap in Orboot. And Linux is now satisfied that these tables are real. And Linux boots and hangs. So we went through all this work, and we had valid ACPI tables. Everything looked good, and Linux booted and hung at APIC timer verification. Now, at this point, we've tested all this with both Coreboot and Orboot and Linux. And I even had, again, a small command line interpreter I built into Coreboot, which is in my branches, which lets us actually set up APIC timer interrupts and catch them. What was interesting, if I had the APIC timer interrupt generate an NMI, it would in fact make it to the core. But for whatever reason, APIC interrupts were being created and not conveyed to the core. All this code had been verified on QEMU, and I know that QEMU is not always trustable for hardware, but for APIC, for the last many years, almost since it was created, it's been good for me for testing APIC code. So something was missing. AMD told us that basically we had all the docs they had, and we had very current docs. So desperate times lead to desperate measures. Here are the desperate measures. Probe all the MSRs. There's only, well, there's not really 2 to the 32 of them, but there's an awful lot of them. And you can't actually directly read an MSR in the way you do a direct in and out, because if you read a non-existent MSR, you take a GPF. That's maybe one of the worst hardware interfaces ever. The idea that you take a GPF for basically looking at the wrong MSR rather than setting a condition code bit or something just amazes me. But anyway, we generate Rust that looks like this. Call function 1. W is a formatted printer to the console. This second parameter is, can't select it. The second parameter is the MSR number. Third parameter is the value it should have. And the fourth parameter is whether it's a read-only MSR. So the function reads the MSR, compares it, prints in a message if it's got the wrong value, and then conditionally writes it if it's not read-only. There only ended up being 192 of these. Once we added this code to Orboot, APIC timer worked fine. So, that's log base 2 of that. It's 8 bisects, and that's the one that makes it go. MSR C001 10E2. There's actually 10E1 and 10E3. Those 3 are not documented anywhere. I have yet to talk to anyone at AMD who actually knows what they do. But it makes the APIC work. So desperate measures worked out this time. The next step, really, if you look at that long hex value, I mean, it kind of looks like it's got fields, can't tell. We could sort of walk through that value with the same bisect approach and see, what goes on, what bit or bits in there enable APIC interrupts to the core, but we have other things to do, so that's going to wait. So this is a really short overview of what had to be done. My main goal in giving this talk was to give you some idea of what it took and where we are. There were 3 separate Coreboot attempts before I decided that it was time to move over to Orboot. It turned out to be a really good decision. Orboot was just a lot easier to work with than Coreboot. Rust is a large reason for that. The thing that fooled me is I had Linux booting from Flash in 2 weeks on that first attempt. So that led to a lot of over-optimism and poor diagnostics of why it wasn't working. There were basically about 2 Orboot attempts. Rust really proved its value here in the fact that we were able to easily import code from an unrelated project, which was a hypervisor called Excite, and use it with very, very little change. The rest of this time has been poking around to get more working and to get this code upstream. So Titus has done a lot of very, very nice work in making it more idiomatic Rust. He's much better at Rust than I am. And to really clean up the documentation on the MSRs we set, all those are now pretty documented as much as possible with the public documents. But we're really happy with Rust and Orboot at this point. I can't imagine doing this over again in C. If there's one maybe complaint I do have about Rust, we're still in early days with the bare metal support, and there's enough churn to make it difficult at times to update to new tool chains. But that said, we have a blessed tool chain in Coreboot, and we probably will end up having a blessed tool chain in Orboot. Recently, I found out last week, Oxide has a CRB. They've reproduced these results. They're right where we are. That was kind of nice to know that another company could take this code really and just have it behave the same way. Unfortunately, up to and including the parts that don't work. Next steps, we'd like to target a system that people can afford. We're looking at that A300, and I always forget the vendor of the A300. It's now called the X300 Mini. We're still not quite there with even loading Orboot yet. We're still trying to deal with how to get the output from the port 80 to any kind of reasonable serial. We'd like to bring more people in. That's the reason for giving this talk. I'm hoping to get one or more people who want to look at this. It is the first time in probably 15 years that we've really talked about having all the code on the x86 for server class platform be open source. I understand that, yes, the PSP is there, and yes, it has a lot of what we would have called firmware, but you've got to start somewhere. I think it's realistic to think we'll be a lot further along and probably doing SMP next year, and it'd be neat if we could even interest AMD. There is a movie of it booting. You really want to run it at 10x. You really want to start it at 37 seconds in. But what you can see in that movie is Orboot loading, doing a lot of printing. There are two places there where it stops, and that's the debug console, and you hit Control D and can move on. There's a trivial debug console that lets you examine memory and hex dump it. And then you'll see Linux boot. You will see Linux fall into the uroot shell, and then we run a few uroot shell commands showing that we actually are up in single processor mode with APIC interrupts, but not UART interrupts. It's a polling-driven console program, part of uroot, called basically console. So thank you for viewing this talk. I also thank 9 Elements for doing a very good job, just terrific job of working through the mess we have with the pandemic. I always look forward to anything 9 Elements runs, and I'm sorry we're not all together in the same place, but this is a pretty darn good substitute. So thanks again.